Hey everyone, welcome. Okay, let's dive right in. Today we're going to build a complete ground-up conceptual mastery of Chapter 2 from your science textbook, Acids, Bases, and Salts. Now, I know a lot of students try to just, blindly memorize the chemical reactions and all those color changes, but we are going to completely strip away that rote memorization today. We're going to visualize exactly what's happening in the beaker, on your dinner plate, and even all the way down at the microscopic level, so you can truly master the chemistry. By the end of this explainer, you won't just remember the facts, you're genuinely going to understand the why behind all of them. Let's get started. So here is our roadmap for today. First, spotting acids and bases. Then, lab reactions and equations. Third, neutralization and metal oxides. Moving on to the power of ions, followed by measuring strength with the pH scale, and finally, everyday pH and salts. Let's actually start with something you've probably seen at home. Imagine you accidentally drop some delicious yellow curry on your crisp white school shirt. When you go to wash it and scrub it with soap, suddenly that yellow stain turns a deep reddish brown. I mean, why does that happen? And then if you rinse it with plenty of water, it magically turns yellow again. This wild color change happens because turmeric, which is what gives the curry its yellow color, is a natural indicator. It is literally reacting to the basic nature of the soap. Before we hit the lab, let's establish our absolute basics. You probably remember from earlier classes that acids are your sour substances, like lemons, and they change the color of blue litmus to red. On the flip side, bases have a bitter taste, and they change the color of red litmus to blue. A super easy way to remember this is simply, base turns blue. But here's the catch, right? We can't just go around tasting everything in a chemistry lab. That is incredibly dangerous. Section 1. Spotting acids and bases, visualizing chemistry. So how do we actually spot these chemicals without tasting them? To safely identify them, we use substances called indicators. And what's really fascinating here is the sheer variety of indicators we have at our disposal. We have natural indicators, like the turmeric we just talked about, or litmus, which is actually a purple dye extracted from a tiny plant called a lichen. We also have synthetic indicators created in labs, like methyl orange and phenolphthalein. And oh, here's a really cool one from your textbook's Activity 2.2, olfactory indicators. These are substances whose smell literally changes depending on whether they're in an acid or a base. Think vanilla, onion, and clove. If you put onion extract into a strong base like sodium hydroxide, boom, you won't be able to smell the onion anymore. Section 2. Lab reactions and equations into the laboratory. Now that we know how to identify them safely, let's see how they behave. Let's look at a classic, absolute must-know experiment, Activity 2.3. We take some solid zinc granules in a test tube and add dilute sulfuric acid. Almost immediately, you'll see bubbles rapidly forming on the surface of the zinc. But what exactly is this gas? Well, to find out, we pass it through a soap solution, creating bubbles filled with the mystery gas. When we bring a burning candle near these soap bubbles, they burn with a very distinct, sharp pop sound. That pop sound is our ultimate confirmation. It tells us the gas evolved is hydrogen gas. All right, whiteboard time, guys. Let's translate that awesome experiment into the language of chemistry. When an acid reacts with a metal, the metal basically displaces hydrogen from the acid. Think of these equations as simple puzzle pieces, just swapping places. The zinc takes the place of the hydrogen in sulfuric acid. This forms a completely new compound called a salt, in the specific case, zinc sulfate, and it pushes out that hydrogen gas we just popped. Now, bases can also react with metals to produce hydrogen gas. For instance, using sodium hydroxide with zinc gives us a salt called sodium zincate and hydrogen gas. But keep in mind, this specific base reaction doesn't just happen with all metals. And then we have an even more important reaction. What happens when an acid meets a base directly? They totally cancel each other out, forming a salt and water. Section 3, neutralization and metal oxides, canceling out effects. Checking your understanding here with a very classic textbook question. Why does your family always tell you not to store sour things like curd in brass or copper vessels? Well, curd and other sour foods contain organic acids, and as we just brilliantly saw in our lab experiment, acids react with metals. If you leave curd in a copper vessel, the acid is going to react with the metal, forming toxic metallic salts and hydrogen gas. This will completely spoil the food and could make you really, really sick. So science is literally saving your stomach here. Section 4, the power of ions, the microscopic level. It's time to zoom way in and figure out what makes them behave this way.
Okay, the absolute crucial point is this. All acids have one major thing in common. When dissolved in water, they produce hydrogen ions, written as H plus aqueous. This H plus ion is the boss. It is solely responsible for all the acidic properties we observe. However, H plus ions actually can't exist alone. They immediately grab onto water molecules to form hydronium ions, H3O plus. Similarly, all bases have their own boss. When dissolved in water, bases generate hydroxide ions, written as OH negative, aqueous. That is the fundamental, microscopic difference.
Now, a quick terminology check, because this trips up a lot of students. You will often hear the word alkali. An alkali is simply a base that dissolves in water. Remember this golden rule. All alkalis are bases, but not all bases are alkalis, simply because some bases don't dissolve in water. Potassium hydroxide and sodium hydroxide are your classic alkalis. They feel soapy to the touch, they're bitter, and they are highly, highly corrosive. Never, ever touch or taste them, as they can cause severe harm to your skin. And speaking of harm, listen carefully, guys. You will often see warning signs on containers of concentrated acids like sulfuric acid or nitric acid. When we want to dilute these strong acids by mixing them with water, we must be incredibly careful. The process of dissolving an acid or a base in water is highly exothermic, meaning it releases a massive amount of heat. You must always add the acid slowly to the water while constantly stirring. If you do it the wrong way around and add water to a concentrated acid, the sudden, massive heat generated will cause the mixture to violently boil and splash out, causing severe acid burns. The glass beaker might literally shatter from the heat. Always acid into water. Here is another brilliant check your understanding question right from your text. If you take completely dry hydrogen chloride gas and pass it over dry blue litmus paper, the color does not change to red. Why? It's an acid, right? Well, the crucial point we just learned is that acids only produce those boss H plus ions in the presence of water. Without water, the H plus ions cannot separate from the HCl molecules. No H plus ions means no acidic behavior, which means absolutely no color change on the dry litmus paper. If you use wet litmus paper, however, the moisture provides the water needed. Ions are formed, and boom, the paper turns red. Section 5. Measuring strength. pH scale. The power of hydrogen. So we know ions are the secret agents here, but how do we measure their strength? Scientists developed a scale specifically for measuring hydrogen ion concentration, brilliantly called the pH scale. The P in pH stands for potens, which is German for power. So quite literally, the power of hydrogen. On this scale, the number 7 is our absolute neutral center. Pure water has a pH of exactly 7. It is neither acidic nor basic. Let's look at how the full scale works, generally running from 0 to 14. This perfectly illustrates chemical strength. If a solution has a pH value less than 7, it's acidic. As you move left from 7 down towards 0, the concentration of those hydronium ions increases dramatically, meaning it is becoming a stronger and stronger acid. Conversely, if the pH value is more than 7, it's basic. As you move right from 7 towards 14, the concentration of hydroxide ions increases, representing an increase in the strength of the alkali. It's basically a simple number line that tells you everything about the chemical's personality. Section 6. Everyday pH and salts. Chemistry around us. Let's zoom back out from the lab and look at the real world. You might be surprised, but pH is literally everywhere in your daily life. Your own body is a working chemistry lab. Your stomach naturally produces hydrochloric acid to aid in digesting your food. Living organisms generally survive only in a very narrow pH range of 7.0 to 7.8. Look at nature. When rainwater drops below a pH of 5.6, it becomes acid rain, which flows into rivers and makes it incredibly hard for aquatic life to survive. Plants are highly pH sensitive too. They require a very specific soil pH for healthy growth. Even animals use this for chemical warfare. A bee sting hurts so intensely because the bee is actually injecting an acid right into your skin. Now let's talk about salts. When an acid and a base neutralize each other, they form a salts and water. But here is a super interesting fact. Not all salts are perfectly neutral at pH 7. It entirely depends on their chemical parents. If a strong acid and a strong base react, they perfectly balance out, giving a neutral salt with a pH of 7, like the sodium chloride, the table salt you eat with your food. But if a strong acid reacts with a weak base, the acid wins slightly, resulting in an acidic salt with a pH of less than 7. And naturally, a strong base mixing with a weak acid yields a basic salt with a pH greater than 7. Let's apply what we just learned. We know the stomach produces HCl, but during indigestion, the stomach produces way too much acid, causing awful pain and irritation. So how do we chemically fix this? We use bases, specifically mild bases called antacids. A very common one is magnesium hydroxide, also known as milk of magnesia. When you drink this, the base goes right into your stomach and perfectly neutralizes that excess acid, giving you relief. It is exactly the neutralization reaction we learned about earlier happening right inside your own body. Here is another incredibly cool biological application. Your tooth enamel is actually the hardest substance in your entire body. It doesn't even dissolve in water. However, after you eat, bacteria in your mouth degrade leftover sugar and food particles, producing acid. If this drops the pH in your mouth below 5.5, your incredibly hard tooth enamel literally begins to corrode. This is tooth decay. So what's our defense? We clean our teeth with toothpaste. Toothpastes are generally basic in nature. By brushing, you are deploying a literal chemical defense mechanism to neutralize that acid and save your teeth. To wrap up, let's look way beyond Earth. Your textbook poses this amazing question. The atmosphere of Venus is made up of thick, yellowish clouds of sulfuric acid. Based on absolutely everything we've learned today, do you think life can exist on this planet? Well, since we now know that living organisms, like us and aquatic life, can only survive in a very narrow, near-neutral pH range, a planet blanketed in highly corrosive, strong sulfuric acid is extremely hostile to life as we know it. What does that tell you about the extreme chemistry of other worlds? It tells us that understanding acids, bases, and salts isn't just about passing a science test. It is the absolute key to understanding biology, our planet, and even the universe. Keep questioning, keep exploring, and master the science. See you in the next explainer.